So this exercise related to the space physics or astrophysics, as well as it's a weekly homework which you have to submit tomorrow. We did the first question last session. Starting with question 2. A year, a month, and a day can be defined in terms of motion of Earth, the moon, and the sun. You can use mic, you can use chat, or you can use screen annotation for any question you want to answer. Using these motion, complete the following sentences. A year is the time for what? How we define a year? It's a time for Earth to orbit the sun. That's good. So here is actually how much time the Earth take to orbit the sun. That is a year. And when you're writing, like example, the name of the planets or star, it should be capital. What is a month? How we define a month? So a month is a time for a moon to complete its cycle. That's good. So a month is a time for the moon to complete its cycle, and which is about 28, like lunar month. When we talk about, so that is about 28 days. 28 days is for one cycle, and it's ended like 29. The next month starts, so we'll say 29 or 30. What is a day? Is a time for what? So Earth, yeah, day is a time for Earth to spin it in its axis. That's good. So as the Earth spins its own axis, that is causing a day. So you should know the differences, like the reasons as well. Then we have Earth, Jupiter, Saturn are the 3 planets in the solar system. Okay. And the table gives the information about these planets. Their orbital speeds are given. Use the data to calculate an average radius of a Saturn. So how we can work out the average radius of a Saturn, as we have the orbital speed for we have the formula that speed at which these planets or these astronomical objects are moving, that is given by 2 pi r divided by t. That's a formula. You have to memorize this. Whereas 2 pi r is actually a circumference of the path, which we consider it's a circular. Practically, it won't be exactly circular, but for calculation, we consider it is exactly circular. So what is the orbital speed of the orbital speed is given how much? It's 3.5 into 10 to the power 4. So in place of orbital speed, we write 3.5 into 10 to the power 4. Then it will be 2. What is the value of the pi? The pi is 3.14. R is the radius which we are finding. And T is the time. But you can see the orbital time is given in years. But the speed was in hours. So we have to convert. What we have to do, we have to convert these years into hours. Because like if speed is in kilometer per hour, time should be in hour. If speed is in meter per second, time should be in second. If speed is like in per day, time should be in days. Speed was given in years, then the time should be in years. So now we have to convert the 29 years into hours, like fine. So how to convert 29 years into hours? So first 29 years. First we convert the years into days. So how many days are there in 20? So how many days are there? That is 365. We'll multiply by 29. Years are there. We multiply by 365 to convert into days. So this will give us the total number of the days. And each day 24 hours are there. So we have to convert into hours. So what we'll do, we'll multiply by 24. Now it is converted into the total hours are there. Then we just R is our subject, like we need R. So this whole is divided, other side will be multiplied. So this whole factors will be multiplied and this is multiplied, the other side will be divided. So it will be 3.5 into 10 to the power 4 times 29 times 365 times 24 divided by 2 into 3.14. This will give us the orbital radius of Saturn. So when you simplify this, it will be about 1.3 exponent 9, I guess, which is in kilometers. So 1.3 into 10 to the power 9 kilometer, 1.4, okay, 1.41. So 1.41 into 10 to the power 9 kilometer. Is it clear, this question? That how we work out the radius of Saturn?
Yes, sir.
Anyone having a question or a doubt in this? Okay, the next question, figure 2.1 shows the alignment of Sun, Earth. If we write the answer in full form, when you're writing, because being a science student, when the answers are too big or too small, you should use a scientific notation. A significant, scientific notation means like represent in power of 10. On your calculator, there's a button E and G. So when you have a very big number or small number, just press this button E and G. Automatically, it will convert into scientific notation. Usually is on the left hand side, I guess the fourth row, left hand side, the second button. So you just press this and it will directly convert into scientific notation on your scientific calculator. Now the next question. Figure 2.1 shows one alignment of a sun to Earth, Jupiter, and Saturn. Like example, they all are aligned. In a figure 2.1, three planets and the sun are in line. 29 years later, the Saturn returned to same position, but Earth and Jupiter are not in same line. Use the data in the table to explain why. So what might be a reason why the Saturn and the Earth may not be in the, like why they are not in the same line? Look, what will happen? As you can see, the table is the time for the Earth to orbit is 1 year. Yeah, they have different speeds as well as they have different orbital time. Jupiter is 12 and Saturn is 29 years. Okay. Now, if we take, for example, we say this is our sun. Say this is our sun. And there is, say, planet X, Y, and Z. Planet X is there. Then planet Y is there and planet Z. Say they are in line with each other. Now, if I say for planet X, the orbital duration, like how much time it will take to revolve around the sun, complete its one cycle, say for planet X, it is 1 year. For planet Y, if I say it is 10 years. And for planet Z example, if I say it is 15 years. So when we work out their positions, for example, for planet X, when we talk about planet X, so planet X is taking 1 year to return back. So if it is taking 1 year, so we can say at this position, how much time when it will complete a quarter, how much time it will pass in the year. So it will be 0.25 years will be there. Then when it is exactly on the other side, it will be how much? 0.5 years. When it is 3 by 4 of its path, then it will be 0.75 years. And then when it completes its cycle, when it returned back, that will be the duration 1 year. For planet X. Like this is how the planet X position changes throughout the year. If the question is after half year, what will the position of planet X? So it will be exactly opposite side. But for planet Y, it is 10 years. So when we say planet Y duration is 10 years, means it takes 10 years to completely move around the sun. So how many years will pass when it is quarter? It completed its quarter. How many years will pass? If it is taking 10 years to completely move around, how many years will pass if it is completing a quarter of its motion? Quarter, not half. Half is here. When it is exactly on the other side, because it has to take 10 years to completely move. So means 2.5 years. So it will take, in 2.5 years, it will be here. In 5 years, it will be here. In 7.5 years, this will be the position. And in 10 years, this will be the position. And for planets, is it clear? The second part? And for planet Z, yeah, for planet Z, how it will complete, like, because it is 15 years, I don't have space to make it separate. So that's why I'm using the same path. But consider it is a bit longer, not elliptical. So it will be 15. It has to take 15 years. So how many years will pass when it will be here? It will be 3.75. Then it will be 7.5 years will pass. It will be here. Then it will be 3.7 because 3 by 4 of it, which is 11.25. So when 11.25 years will pass, it will be here, and 15 years pass, it will be returned back. That's how we divide the positions, or we mention the position of the planet according to their cycles. So the previous question was why, like after 29 years, Earth, like they mentioned, three planets were there: Earth, Saturn, and Jupiter. Earth, Jupiter, and Saturn. They are saying why they cannot be aligned after 29 years. So what are, use the data from a table to explain why. So data from the table shows that they have different orbital periods. So as they have different orbitals period, after a duration of 29 years, the Earth, when the Earth is moving, like Earth will move about 29 times. When the other Saturn will move only one time. And Jupiter is like after 29 years, it's about like it will revolve about 2.4 times. So they have different orbital periods. That is one thing. And the second mark is for mentioning, because you have to use the data. In 29 years, the Saturn will move one time. Where the Earth will rotate how many times? Earth will rotate 29 times. And the Jupiter, how many times it will rotate? Because the orbital duration or orbital time for the Jupiter is 12. So it is like 29 is a total divided by 12. So 29 divided by 12, which give us 2.4. Is it clear? This one? Anyone having a doubt or a question till this point?
No, sir.
In the next question, we have to complete figure 2.2 to show the position of three planets exactly 6 years after the diagram. Look, first we will draw a rough diagram like the positions. Earth is here. Then we were having Jupiter. And the last one was Saturn. Okay. So I'm writing here Earth is E. And for Jupiter J and Saturn is S. Now, for Earth, if you check, like 1 year is the duration because Earth year. So 1 year, in 1 year, the Earth will return back. So because after 1 year, Earth will be here. After 2 years, when Earth start, after 1 year, Earth will return back to its same position. After 2 years, Earth will be here. And they're spinning anti-clockwise, the rotation. The direction is not to, like direction is given as shown. So we have to take according to that. According to the figure clockwise, we have to take. So this is 1 rotation, 2 rotations, 3, 4, 5, 6. So means after 6 years, Earth will be here. Is it clear? Earth will be at the same position because Earth take 1 year to completely move around the sun. So after 1 year, Earth will be at the same position. Then after 2 years, 3, 4, 5 until 6 years, it will be again at the same position. But what about the Jupiter? When you check the cycle of the Jupiter cycle is 12 years. Like it takes 12 years for a Jupiter to move completely. So if this was 0, how many years Jupiter will be here? Because it is 12, so means this will be 3 years for the Jupiter. This will be 6 years for the Jupiter. This will be 9 years. And then again, in 12 years, it will return back. But in the question, we just need exactly after 6 years. So where the Jupiter will be on the opposite side after 6 years. That will be the position of the Jupiter. Now for Saturn, position of a Saturn, the duration of a Saturn, like 1 complete rotation is 29 years. So Saturn start with here. How many years will pass if a Saturn is at this position? Because half of 29 is 14.5. So 29 divided by 2 is 14.5. So after 14.5, it will be here. And after 7.25, it will be here. So this is 7.2 because like Saturn is taking 29 years to completely move. So after 7.25, it will be here. Then after 14.5, it will be exactly on the opposite side. After 21.75, because like every quarter is taking 7.25. And then again, after 29 years, it will be back here. So the question is after 6 years. So as it is moving in this manner, so after 6 years, somewhat it will be closer to this line. So what will the position of the Saturn after 6 years? It will not be exactly 7.25 or it will somewhat closer to this region. So this will be the position of the Saturn. Is it clear? How we predicted the position of different planets for the same time interval?
Yes.
So in question 3, table 3.1 lists some of the planets in our solar system with their average distances from sun. You can see the order is there in decreasing. So it's like you have to name the planet. So we have Mercury, then which planet we'll have? Complete the table by writing the name of the missing planet. So we'll have Venus, then Earth, and after Earth we'll have Mars, and then Jupiter. And those planets which are closer to the sun are moving much faster and they have a shorter time, orbital time. Like Mercury is about like 88 Earth days. So like after 88 days, it will return back to the same position. Then as a planet moves around the sun, the distance between the Earth and Jupiter changes. Use the table, calculate the smallest and the largest distance. How we can do this? Look, when the planets are on the same side, they will have the smallest distance between them. And when the planets are on opposite side of the sun, they will have the maximum or the greatest distance. So this is representing our sun. And we have Earth. This is representing our Earth. And this is representing a Jupiter. So when they are on the same side, the distance between the planets will be minimum. But when the planets move in, like when they're on the other side, the distance between them will be maximum. So if we want the smallest distance between them, we have the radius, average distance from a sun is given like the distance between the sun and the Jupiter is given, and the distance between sun and Earth is also given. The distance between the sun and Jupiter is 7.8 into 10 to the power 8 kilometer. And the distance between the sun and the Earth is also given, which is also known as 1 astronomical unit, which is 1.5 into 10 to the power 8 meters. Now we need this distance. How I can find this distance? The distance between Earth and Jupiter. I can find this minimum distance between them. So what we
Sir, by
simply
subtracting their average distance from the sun.
We'll simply subtract to get an average distance. That's right. So it will be 7.8 into 10 to the power 8 minus 1.5 into 10 to the power 8. So when you subtract, no, we are not considering because all the distance are given from the center. It's not from the surface. These are the distance from the center. So we don't have to consider the diameter of the sun here, as it's not given at all even in the question. So the distance between the sun and the Jupiter is given, sun and Earth is given. We just subtract. So we'll know the minimum distance between the sun and between the Earth and Jupiter. Which is about 6.3 exponent. So the minimum distance will be 6.3 into 10 to the power 8 and the unit will be kilometer. Now, when we'll have a maximum distance between the two planets when they're in the opposite side of the sun. Like if this is representing the sun, Earth is example on the right hand side and the Jupiter is on the left hand side. Now this will result the maximum distance between them. So we know the distance between the sun and the Jupiter, and we know the distance between the sun and the Earth. So this distance was 7.8 into 10 to the power 8, and this distance is 1.5 into 10 to the power 8. Both are in kilometers. So we want this distance from Earth to the Jupiter. So what we'll do, we'll simply add them. So it will be 7.8 into 10 to the power 8 plus 1.5 into 10 to the power 8. So when we sum, it will be 9.3 into 10 to the power 8 kilometer. Is it clear, this one?
So what if they ask us the largest or smallest distance between Mercury and any other planet?
Same way we will do. Like example, if they ask what is the smallest distance between the Mercury and the Jupiter, so you will subtract like the distance between the Jupiter and Sun and distance between Mercury and Sun. You subtract and you get that distance. That is the minimum. And when
but in the Mercury, it's the 10 to the power of 7, and the rest are power of 8.
No difference because the Mercury is closer, so the value is smaller. But you can subtract. Subtraction can be done. Like you can subtract 5.8 exponent 7 with 7.8 exponent 8. It can be done. You will get the answer. Only exponent shows like 5.8 exponent 7 shows that the value is small. When exponent in a positive is smaller value, that means the value is smaller. That's only. Like it's like 5, and then there will be how many zeros will be there? 6 zeros will be there after that. Is it clear? But it will be done. You will do or
Yes, sir.
solve
Thank you.
in the same manner that finding the distance between the planets. If you need a maximum, you add, and if you need the minimum, you subtract. So for a minimum smaller distance, we subtract the two distance from the sun, and if you want the maximum, we add. A planet is in orbit around a distant star. Like there is a star, for example, we are observing the star. This is the direction of the motion. As it passes in front of a star, it blocks some of the light. And it is obvious, like example, if this is representing a planet is there, so this is representing a planet. When this planet start to move, it will block some of the light. And then when it crosses, then more light, because like if say we are observing, like on your screen, you're looking at the say a star is giving out light, but when the planet move in front of this star, the amount of the light which you receive start to decrease, and then it will increase. So figure 3.2 shows an incomplete graph how the brightness of a star vary with the time as seen from the earth. Like when we are observing, the planet is in front of a star from T1 to T2. What does it mean? Like example, when the planet reaches this point, it start to block the light, and it continue to block the light until it is on the other side, until it's here. From T1 time to T2, it is blocking the light, and then it again the light is coming to us. So we have to complete this sketch to show a brightness of a star as seen from the earth. So what will happen to the brightness of a star? Because it will block the light, so we'll have like less brightness. And when it is like when the star is between when the planet is between the star and us, then the brightness will decrease. And then when it crosses, then again the brightness will increase. So we'll observe the same brightness of the star. Is it clear?
Yes, sir.
Yes, sir.
Shouldn't we? No, it should not be slope. Why it should not be slope? Because look, the size. Why it should not be slope? It just like when the planet just cross the star, the amount of light, like example, if I say the light intensity, say you're receiving, say 30 watt per meter square, the amount of the light. But when this planet will be there, then the amount of the light, like this is representing you're receiving 30 watts per meter square. But the moment this will block, the position does not matter because it will block the same amount of light. The planet will block the same amount of light in all these positions when it is here, here. So it's not like the amount of light which is blocked. If the planet size was increasing, then the amount of a light which is blocked, that will also change. But here what happened, the amount of a light, because the size of a planet is same, so the amount of light it will block in this time interval will be same. Once it crosses, again it will be a flat line. So you can make like, for example, when it enter, you can make a small slopes. When time t1 is there, it start to block, then amount of a light which is blocking is increasing. So as the amount of light it block, it increase. So there will be a suddenly small change you can make. And then there will be a flat line. And from once it crosses, it will be, you can draw like this, or you can also draw, or but not like this. This is wrong. Why? Because if you're drawing that in amount of a light which is blocked by the planet is increasing, that is wrong. Why? Because the size of the planet is not changing. That's why the amount of a light which we receive from this star will remain same. So you have to draw a horizontal line which shows that the amount of a light which we receive is decreasing. And then once it crosses, again you receive the same amount of a light. Is it clear, this one? Yeah, you can draw a horizontal line anywhere,
Yes, sir.
as they did not mention how much light is being blocked because it's a sketch. So in a sketch, you can draw a horizontal line anywhere. It can be near the bottom. It can be at the center, near the center. Then describe how the completed figure 3.2 show the change in a change to show a large planet passing at the same distance in front of the same star. So if a large planet is passing, like example, this was a one of the planet, but for what if there was a large planet is passing? Then what we'll observe? What change we'll observe?
So the brightness of the star seen by the Earth will decrease.
Yeah, or there will be a greater decrease, or it will have a very low brightness. The brightness cannot be zero because like planet size is not bigger than the sun. So it, or even the, as they mention here, the first part they mention the planet is smaller than the sun, like the star which we are observing. So if the brightness cannot be zero, it will decrease. So if a large star is passing, what we will observe, if a large star is passing, we'll observe that there will be like a small lower brightness will be there. And it will take the second point is, look, when a small star is entering, when a small star start to enter at time t1, because it will take short time to just enter this region, so the change in the brightness for time t1 and change in brightness for time 2 will be shorter. But if the large star entering, like there is a large star and that start to enter, so it will take longer time to change the brightness, and then again it will take longer time to change the brightness from t1 and t2. So 2 points are there which you have to mention as it's of 2 mark. Number one, that it will have a lower brightness and it will take longer time to decrease and increase the brightness. Because when it is entering, it will take longer time. When it is leaving, it will also take longer time. That's why. Is it clear?
Yes, sir.
Then suggest how an astronomers use the change in brightness of a star to measure the orbital period of a planet. Like how they can work out. What if the big planet is closer to sun than small in case? Yeah, the time will be different. So basically what they will do, they will look for, if you want to work out the orbital time period, because orbital time period, like time, this thing will happen again. So for example, if there is a, for example, there's a planet which is moving around. So when it complete, like one time it completed, increase and decrease, and then it returned back and again it start, like what, if you want to work out the orbital period, like how much time it will take to move around this star. So when they start to decrease, we start the timer, like we start recording the time. And when again it will start to decrease again, we'll stop the timer, because that will be the time taken by the planet to move around the star, or that will be the orbital time. Is it clear how we can work out the orbital time, time taken by planet to move around this star? So what we, if we want to measure a time, for this planet to move around the star. So when this brightness start to decrease, restart the timer. And then when again it happen again that the brightness start to decrease, we'll stop the timer. That is actually a time taken by this planet to move around the star. Is it clear? Any doubt, any question in this?